Okay, cool. So I think it's now recording. Yeah, perfect.
Okay.
So we do what we do because I had here because I was playing you. I mean, you were saying you were getting stuck at 17, and I was just playing because I couldn't remember the level 17. It's fairly straightforward. You passed 17 through 19.
Yeah.
Okay,
I
cool.
got 17, 18, and then 19, and eventually 20.
So
yeah.
we can do
Yeah, I'd
20.
just say let's do 20. Yeah.
Okay, cool. So we can do 20.
It's gonna force us to get better at recognizing unitaries. That's for sure.
Yeah, I mean, let's see. So I can't remember where I got. The first thing I usually do is I go and I just go straight and do a check.
Uh-huh.
Because this kind of tells me
Yeah.
I changed my approach a little bit, but yeah. So
you know it's not a C. We know it's not a C naught, right? Because like a controlled gate would have an identity. Like if it were controlled on the 0 qubit, we'd see a 1 in along the diagonal of the matrix.
yeah.
So I think, I mean, and if we look at the block sphere, I know I learned that trick from you where if the block spheres actually make sense, then you know you're not entangled. So
yeah.
So,
but I mean, I forgot how to. By the way, did you the order in which the vectors are? This is following the Kiskit order or the
right?
Oh,
it does. So I was
it's probably Kiskit order.
It's still probably Kiskit order, right?
I was going to mention that we should. Yeah, so we need to swap the second and third columns and the second and third rows of the matrix before we
of the matrix.
Start to.
Okay, that's good to know. Well, it helps if it's if the matrix is
But this is for the matrix.
What's the term?
But this is for the matrix. So for the state vector is the same as well, or the second. So because if I do a
I think to swap the second and third elements of the state vector as well.
Yeah.
Because if I do.
You do 1. Yeah, your state vector.
No, how do I even get there? I'm just trying to get.
Let's make sure. So X. Well, yeah. What if you just do X? Let's make sure that because that would show up in the.
Yeah. So if I do X on qubit 1, that goes here. So this is yours.
Hadamard on qubit 0, and that's about it, I think.
So if you do Hadamard
on qubit 0.
Yeah, I think you were trying to figure out where
the other way.
The order, yeah.
Yeah, I was trying to figure out the order, yeah. But I mean, Hadamard of qubit.
Probably 1, then let me see.
So if I'm what were you saying, Giri? So if I go to apply Hadamard and qubit 0, that is basically these.
Right, but could you try it on 1 instead?
That doesn't because that keeps the 0 here. So
something's weird. Hold on.
So if I apply these, and this is kind of 0. I mean, you guys can also work on your own notebooks, right? Like if you want to play with other ideas.
So Hadamard on 0 and X and the NOT gate on 1 should do it.
But that's what I tried before, and okay. Weird. I thought I had tried it right before and it didn't work out. But that gets us because that basically.
Yeah, but the issue there is we're missing, like it doesn't match up on the unitaries because like if you look in column 2, right now we have the real components; those need to shift over to the imaginary.
Right.
Yeah, but you can do that with a Y gate, right? The question is because that's what the Y gate. Like if I just start with like so this is the initial state vector. If I apply a Y gate to 0, right? Like what this does is it basically does in Quirk, right? Like it moves the amplitude entirely to 1, and it shifts the phase by 90 degrees, which basically means that your 1 goes from the real to the imaginary. So, but how would that work here if I...
So what I like to do usually is I look at the columns of the target unitary and I map them to the input states. So I look at what 0, 0 as an input would give on the output and what 0, 1 would give as an output. And I just try to figure out what gates would match all 4 inputs to their output.
So that's a good point. Yeah. So,
but that's what we're...
Yeah.
Mm-hmm.
Go ahead.
No, I was saying that so we have the two differences are the 2 middle columns, right? But then the last column also has a sign difference.
Oh yeah, you're right. Yeah, that needs to change.
And so and we said the second column is for the state 1, 0, correct?
For 1.
Yep. Yes.
So the state 1, 0. So there must
that's
be
because of Qiskit ordering. It's not 0, 1. Okay, so it's 1, 0.
It's 1, 0. So this means qubit 1 in the state. So what if we would do? I don't know. Let me try. What if we would do a sort of a control? No. Like if we want to target just that state, right? Like the same way with the controls that you can target like one specific state, the phase of one specific state. I'm thinking about, but that wouldn't work with a control Y, would it? So if I have a superposition,
good point. Yeah.
If I have because then we need another type of control. I think if we have a superposition like these, and I say, what is these doing? So for example, a control Y here flips the phase of 0, 1 and 1, 1. So it flips the phase. Yeah. So okay. It's not that if it applies Y, of course, and the qubit. Yeah, that makes sense. Sometimes I have, it's really hard when you think about controlled operations because you can think of them in a classical way, like when qubit 0 will be 1, then this gate will be applied to qubit 0 to qubit whatever. But with the controls, that it makes a lot of sense to think about it from at the state level, the system level, right? So if you have a control set, it's like that's gonna shift the phase for the state 1, 1, and so. But this changes. That's not gonna do. I think that's not gonna help because that will change. I mean, let me try and see what happens. Okay, so if oh yeah, but how to implement a control Y in Qiskit?
So it seems to me like qubit 1 always gets flipped between the input and the output. Just going by the unitary matrix. So I just wrote down what it would look like. I can show you that on my screen.
Okay, so 1, 0, you have that going to.
I can make because I'm sharing the screen. I can make it.
Oh, did you when you wrote that down, did you also flip you said you flipped the second and third column and the second and third row?
All those, yeah.
Oh, okay, yeah. Yeah, that really throws a wrench in the works for me, like having to flip that. I mean, it's
inconvenient, yeah.
Yeah, it's inconvenient for sure.
So it looks like the states that have a phase factor of I are the ones where the qubits are different. So you start off in 0, 1 or 1, 0, and the output states have a phase factor of I attached to them. 0, 0 and 1, 1 don't have that.
So the states that have the phase of I are the states where the two qubits are different. Yeah. Yeah, I mean, you can see, yeah, exactly. I mean, you can see this here, right? So it's the 0, 0, and 1, 1. You can see this in the...
Yeah, exactly.
See if that works.
Do you think this is easier to solve as with both qubits instead of thinking about what's happening to each individual qubit?
That's what I'm trying to think. Like from a because what we have here now is that something happens to the states as Giri said, where the zeros and the qubit 0 and qubit 1 are different.
Yeah. Let me just verify, Giri, let's say on the first column. So this is where 0, 0 is going to, and it's going to 1 over root 2. If I'm flipping the second and the third row, are we starting with 0 as the index? So when you say flip the second and third column, those are the two inner columns.
No, I mean the middle two columns and the middle two rows.
Okay, cool. Yeah, that makes sense. Cool.
Yeah, that's because 0, 1, the only states that would be affected are 0, 1 and 1, 0, because the ordering is different. So 0, 0 and 1, 1, it doesn't matter.
Yeah.
But does matter for the other two, so we swap them.
I was trying to prepend or append, see if we could see something at the qubit level. I mean, if we append it, we're obviously matching the state.
Yeah,
because
I think that's.
Mm-hmm.
Well, I think that's where you found we already passed the first two checks, but then
exactly.
We're off by a phase.
Yeah,
so.
yeah. So that's not going to help.
Well, so then I wonder how hard is it to? Well, yeah, that's the thing. It's not just it's like how can we? What I'd love to learn is the intuition around knowing how we want to affect the phase for this whole state.
Exactly. So so you can. So we can do. I mean, what you can do, right? Like you can have. You guys see Quirk now. So if you can target specific phases of specific states with control Z variant, right? So if I do like a control S, right, that's only going to phase by. So it's only going to phase by 90 degrees the state 1, 1, 1, right? Because this is the equivalent of a 1, 1. If I would sandwich all this with not gates, then it does the same for 0, 0.
0, 0, yeah.
Okay. If I instead of that I leave the sandwich only on the qubit 0, it does this for 1, 0. So maybe that's something that we could try in here. So we're saying, but how can I in Qiskit? How can I implement a control? There's no native control S, is there? It's just a control Z.
Oh well, we know that's not the case because we know the gate set that was used.
Oh, of course, you're right.
And I think for 20, if you scroll up,
yeah.
I think
So you have a control X.
It's only you do have a control X. Now I don't know.
So with the control, so what you can do if we have a control X, and we also have. Let me see if I remember this well. So because a control Z is the same like a control X, where the X is sandwiched by Hadamard's, correct?
Yeah.
So, and what other gates do we have? Okay, X, Y, STG, okay. Maybe it's just, I mean, what would a control? So if I do that with a control I, it's not doing what we want. Because we do have the the S and the SDG and the S dagger and the D dagger. I'm trying to think how could we use them. how could we use them in combination of control X? Well, first of all, what would happen? Just to maybe get something moving. So if we do control X on 0, 1, okay, then we're not matching obviously that anymore. But
Okay, we just shifted.
What has happened now?
Well, so now 0, 0 goes to both 0, 1 and 1, 0. Yeah. And then, whereas before it was going to, was it going to 1, 0 and 1, 1?
0, 1 and 1, 1.
Sorry, 0, 1, that's the flip. Okay, 0, 1 and 1, 1. Now, one thing that, even though we know the final outcome isn't entangled, it doesn't mean that there aren't two CX gates in there. I just wonder if there's an operation we would do while we're entangled, and then we would, there would be another CX gate.
What do you mean?
Okay.
So, well, I know with some circuits you can entangle and then do operations while you're entangled, and then you can disentangle. Yeah, like with, well, I mean, I guess that's what even Grover is doing at some level.
So you mean that?
Oh no, but Grover doesn't disentangle the qubits. But like, if you look at like some of the, what is the, like if the simple SAT solving examples, they'll entangle just to do a Z rotation and then uncompute all the, like everything except the final control Z.
Yeah.
Yeah. Anyway, I don't know if that's, I mean, that would be, it's possible maybe this circuit picked out, randomly. But let's also see how deep this circuit is, because that will give us some ideas.
It's depth 2.
Oh, wow. Okay.
So that's the thing, is it should be fairly simple, right?
This should be fairly simple then. We just need to get those, adjust the phase.
We could almost brute force it.
We definitely could do that.
It's like,
I was hoping we were going to think through some of these.
Yeah, I know.
Well, so, I mean, here, let's look at the pattern. So we know the second and third column here need to shift from reals to imaginaries. And so the Y gate is our friend in that, I think.
Exactly. I mean, what if we do these, right? No, that's definitely. So, okay, so now we.
But see, now shift it. Oh,
yeah,
okay.
but now we got the second column right, didn't we? Don't we? Yeah.
Did we though?
Yeah.
Oh, well, but we still have an odd phase in there. Oh wait, no, we got the second column right. The third column is now wrong.
The third column is missing, exactly.
Okay, so what do we do with that?
But why, wait a second, why did this happen?
Oh, but that.
So why does a Y behave like that? Because the Y does the same, like the X, right? But it just also, at the same time flips the phase by 90 degrees.
Yeah.
Yeah.
So.
Okay. So now we have the third column and the fourth column, and those now both need to switch as well. From reals to, oh no, sorry, they already are in imaginary. Okay. Oh no, sorry, the fourth column needs.
The fourth column needs to be.
So that's 1, 1.
But I think that's the effect of the Y, because before that it was in the real part, exactly.
Oh, it was in the real. Okay, so we're swapping those two.
So the problem, yeah, because that's obviously the 1-1 state, and so the last column is the 1-1 state, and so
Okay, but that also changed the.
it's like that's the problem that I'm having, is that if we just apply operations to single qubits, you're always going to change 2 columns at a time.
Yeah.
Right?
So I think this is good. So let's to build our intuition when we see, like if you were ever to just see a unitary this way, you could spot those things. So what the I guess the pattern is we are seeing those switch.
Because I see we also now lost column 0, right?
Oh, we did.
Yeah.
Yep. That's not good.
So maybe the starting with the Hadamard is not the right. So the Hadamard gets us these. What if we start with a Y? What is it gonna change? So if we start with a Y, and then we apply a Hadamard, where are we now? No, it's not close to. Because here we're in the first column, we're imaging it. We're still in the complex part, and the second column. Because the first operation is going to be a Hadamard, right? I mean, but maybe it's a Hadamard in the first qubit. I'm trying to get us, maybe to a point where where it's easier to see.
And what happens if you put a Hadamard on both?
Well, then
I'm not sure that makes sense, because
no.
Yeah, because
There's a lot of zeros.
State, there's only 2 in the output state, right? It's not a superposition of all of them. There's a lot of zeros in the matrix.
Exactly. So the Hadamard must be just in one of the qubits.
One of them. It's probably the first one.
By first one, you mean qubit 1 or qubit 0?
Yeah, no, qubit 0.
So this is only depth 2. So yeah, then I wonder. So what happens if you put a Y gate either before or after that H?
So if we have it before on qubit 0, right? I think that takes us away, because I mean, even the state vector is not matching. It's like it's the like we have in the first column, there's they're in the real part.
Yeah. Okay.
Where have we got? So we've got only it's what Giri was saying at the very beginning, right? So the complex part is only in the 1, 0 and 0, 1 states.
Yeah.
So there's got to be, maybe this is some sort of phase kickback in the sense that there's got to be a control knot, because a control knot on a
you're thinking if you have on the first qubit you have. Oh, but no, we don't have that many instructions.
No.
If you're talking about a phase kickback where you start the second qubit and you want to get to the negative X state. Yeah.
Mm-hmm. So with the Hadamard's got to be somewhere, right? So this for sure.
Definitely.
And so what did we say? What does an next CX gate do here? It just flips the columns, right? That's my current unit. So it just takes the last column. Oh, no, nothing. The last column is real, it's not complex.
Yeah.
I kind of liked where we got just with these, right? But it does not.
Just those two. Yeah.
But we might just be a dead end because this is the closest we've got.
What if you do? Oh no, we already have a 1 on the X. I was gonna say, what if you just do a CY, a YX on one of the qubits to rotate by
You mean
90 degrees?
So what gate?
Kind of what I was talking about. Yeah, what I was talking about in the chat earlier.
A Y gate on one of the qubits.
Yeah, but
a Y and an X and an X and a Y.
Yeah, Y and then an X. Yeah, just to. Well,
the problem is that with the Y, we're kind of, doesn't matter where we apply it, we're going, because here, so if a Y and an X.
So I think there's one way to get the phase shift only when the qubits are different, and that could be to apply the S gate to both the qubits, both qubit 0 and 1.
Oh, because then those
phase.
Because then they
both cancel out for 1 1. For 0 0 they do nothing. For 1 1 they cancel out, and for the other two you end up with a phase shift by I.
So what do we have here?
Yeah, but before and after that, we still have to figure out what to do.
So if you apply, if you apply,
could you try this out? S on both, and then Hadamard on the first one. Hold on.
I mean, you got to start with a Hadamard, like.
No.
Isn't
apply
that
the S first, and then apply the Hadamard and the X.
With the S on what? But if I start with the S.
Yeah, that's what we want. So S on 0 and 1 first, and then you can just move the Hadamard and the X below the two S gates.
But an S on the 0 won't do anything without the Hadamard.
Exactly. I think those two first, they won't do anything. Oh, what?
Yeah, but no, in the sense that that will work because.
But it solved it, right?
Yeah, and I'll tell you why. Because
but why?
We think they don't do anything, but they actually introduce they just introduce a global phase, right? So they introduce the global phase, which we sort of ignore, but we actually need it here, if you think about it.
So it introduces.
I can take you through it. So if you start off with 0 0. Yeah. So when you start off with the S gates on both the 0 and the 1 qubits, right? You on the 0 0 and the 1 input states, you don't get the factor of I. You just get either a factor of 1 or -1, right? But on the 0 1 and the 1 0 states, you end up with a factor of I. And that's where the global phase comes in at one. And after you have the global phase, if you apply the Hadamard and the X gates, that pretty much does it for you. So
yeah, so I know. Okay, so I know what you're saying. So I mean, the thing is, it doesn't matter, right? Like from a practical perspective, it doesn't really matter. But if you try to match the actual unitary matrix, there's a difference between. There's a difference between this unitary matrix and this unitary matrix. Yeah.
Yes, exactly. Yeah. So I mean, they're pretty much identical in Yeah, so if you look at these two matrices,
Okay.
right, I mean, they're pretty much the same except for a global phase factor on some of the states, right? So, yeah, so if you just look at this matrix here, the only difference between the current unitary and the target unitary is, I think column 2 has a phase factor of I, and column 4 has a phase factor of -1, and column 3 has a phase factor of I,
Yeah.
right? You can confirm that.
Yeah.
So, I mean, if you take your current unitary and multiply the first column by 1, the second column by I, third column by I, and fourth column by -1, you get pretty much the exact same thing as your target unitary.
Yeah. So all this is saying is, yeah. So all what you're saying is exactly that. The difference is there's just a
It's just
phase.
global phase.
It's just a global phase difference.
Mm-hmm.
Do something for me. Just just have the two S gates and let's take a look at the matrix
Right.
with that.
Yeah. So look at this. It has those minuses in places where.
Yeah. So if you look at this, you see that no. I mean, this is what matters, because the first column is just 1, the second and third columns are I, and the fourth column is a -1.
Yeah.
And that was exactly the difference between your when you had the Hadamard and the X. Those were the factors that were missing from each column, right?
Yeah, because the two S's consecutively add up. That's actually, Amir, that's kind of what we were saying in the chat before, right? Like because the 1 state has two ones, the two S phases, they pile up to become like an actual an actual Z phase, like a 180 degrees phase.
Right.
And so. Yeah, it somehow feels like I understand it, but like it still feels like there's something I should take out of that, and I'm not really like the intuition for me here would be like, how can you see there is a global? How can you easily see there's a global phase difference between unitary matrices? Is it just?
I mean, I looked at the matrices and found that out, but apart from that. I mean, I didn't see a way to introduce a phase factor only on the 0, 1 and the 1, 0 states, especially given the gate set that we had, right? We didn't have any controlled Y gates or anything of that sort. We just had, with the gate sets that we had, the only way to introduce a phase factor was to use the S gate or a Y gate, but that didn't seem to work either. So sort of trial and error towards the end.
Mm.
Well, I mean, here's something that's telling. Like, if we think about the 0, the first column and where that vector is going to, like it's the identity, but like there's still that fourth row which has that negative value, and that's going to be consistent across every vector that's going to every other vector, even though it's still the identity. So then you can pull out that global phase of -1.
Yep.
And like we know with, normally we won't be able to inspect things this way, but like we know global phase factors don't matter to the end result.
Yeah.
Something else too I made a mistake on was when we were looking, I was like, but those two S gates aren't going to do anything.
Yep.
Because I was thinking of this, I was thinking of the initial state, but we're looking at the unitary, which is the transformation. It's not,
So this exactly.
Yep.
Yeah. Yeah.
Now here's a fundamental question: should we be challenging ourselves on something that we hear time and time again? Global phase factor does not matter. So yeah, we. Like,
it matters. There's one thing. So I think it actually matters. So it matters in the sense that if an operation carries a global phase, that global phase is the one that's kicked back on a phase kickback.
Mm-hmm. Yep.
So this is an important. I mean, I still haven't really kind of. I just said that because I know it's it's true, but I haven't really played a lot with these to kind of feel comfortable, right? But if you take a look at Quirk and take a look at the the tooltip here, for example, the Hadamard gate, right, has a global phase of 90 degrees, right? Like of I. It says at the very bottom, global phase. So if I do a control Hadamard like that, what is this doing? Or am I doing this wrong? Exactly. You got to do these. I think I don't know. I don't even know where I found that, but it's because of one being kind of like an eigenstate of the Hadamard operation. Then this phase kickback gets in there, right? Like, no, I'm saying something wrong. Or I'm not showing it right. But there's something the global phase is then something that, you know, with the phase kickback, it's got something to do, or it actually creates, it's the phase that you're kind of kicking back, but I don't know how would you show that.
Well, I know if you have a plus and a minus for those two, and then you use a control X, you're going to get the phase in the first qubit. So if you switch that, that's like the prototypical one, I think.
Sorry, that's because that I'm doing. It's not a Hadamard I should control. Is the phase kickback happens with a control X, not with a controlled operation. So yeah, I know. So the global phase in here.
Yeah, but I think you need the negative on the other one. So you need a positive on the zero, the first qubit, and then a negative on with that. Or
all right, sorry, I know what you mean. So you need exactly these. Yeah, exactly.
That one does it. Yeah.
But it's still not 90. There's something wrong with what I said in terms of these being 90 degrees. Because here there's a phase of. It's introduced a phase of 180 degrees, right?
Oh yeah, but that makes for this circuit that makes sense, because now the top qubit is would be in the negative X base, or sorry, negative X basis.
Yeah, but I was trying to find a relation between the global phase and the concept of the global phase of the Hadamard being 90.
Oh, I see. You're saying because that's inherent to the Hadamard.
Exactly. That's the point of that's why I said it actually matters that whether an operation has a global phase or not. Like it doesn't matter if your system is in a phase that is globally equivalent to another one, but if the operation carries a global phase, that matters because it can have phase. It impacts phase kickback results. But I was thinking. But I was, because I remember exploring these really early on, but I can't. I'll definitely have to do something more in there. But it's because here it says global phase 90 degrees. And that's what kind of doesn't, that's what I'm not like. So the S gate has 45 degrees. So what if I, yeah, but that's not, I gotta find a better way to show these somehow, or to play with that.
You could start off with plus and minus and apply the controlled NOT.
Yeah, I mean, that's, so this, right?
Yep. That's pretty much the fundamental example of phase kickback.
Exactly, but what I'm trying to understand is like this minus, right? Like this minus, so okay, because the minus carries a 180 degrees phase, and that's the one that's kicked back to the plus state. But what I'm trying to find is a relationship between these and the tooltip telling me that the operation Hadamard has a 90 degrees phase.
Okay.
global phase. That's what I'm trying to find. I'm trying to find, okay, so if I know what a global phase of an operator is, what should I be careful with? You know what I mean? Like, or what are what are the effects that these global phase that is associated to the gate can have?
What global phase does the S gate have?
45 degrees.
45. Okay. So
90 degrees, I think.
It phases one by 90 degrees, but the global phase.
Global phase. Okay.
The global phase of the operation itself is 45. I mean, I hope that I'm reading this correctly, right? It says so exponential 45, and I don't know, I guess complex, but
I mean, that's just the complex representation of the gate, I guess. That's e power.
yeah, that's just the way. Yeah, exactly. So it's just that's just e.
I by 4.
Yeah, it's e to the power of. Okay, cool.
Yeah.
So that's kind of the only thing that that I wouldn't know how to. Because it's when you control. I think it's got to do when you exactly. So when you control an operation, I think I'm starting to remember that when you control an operation, and the qubit where you apply the operation is in one of the eigenstates of that operation, right? The eigenstate of an operator being the state that the operator doesn't change, right? So if for example. That's why the eigenstates of the Hadamard operation are 0 and 1, because, no, wait a second. It's not that it doesn't change that, it's that it doesn't have, it only applies a global phase. Oh, I think I'm getting too confused right now, but it's, I promise you I'll share some links afterwards. But there's let me see.
well, so if I'm hearing you correctly, would it, like when you stack operators after one another, can you, if there's like an inherent global phase to them, are you able to cancel that out?
This is what I'm not.
Or does it not work that way?
I don't think this works. I'm not so sure. I'm definitely getting lost right now. It's got to do. So what I kind of feel is that it's got to do with what happens when you control the operation for within a specific state, or on a specific state. Because I remember reading that in the O'Reilly book. But I can't. I'll probably have to check that up. Because the control Hadamard. Yeah, let me check that, because I don't wanna put it up on the screen just in case I share it, because it's a paid book, so I don't wanna share something that then I get in trouble or something. But if I because that's bothering me a lot right now, because I have the cloud reader here, and this is something that in the book there's a chapter about phase estimation, and they actually explain it this way. Let's see if I can open it up. But it's funny how just that like little thing made the level really difficult, right? Whatever, it's not logging in correctly. I don't know why. I'll have to look it up afterwards. I'll definitely do some more extra videos on these. But there's the notion of that a gate has some kind of a gate, or an operator has eigenstates, in that there are a set of states for which this gate, the only thing it does is apply a global phase, but it doesn't do anything else to them, right? And if you apply this gate to one of the eigenstates and you control it on, and there's another qubit that you use as a control, then that global phase gets kicked back to the other qubit. That inherent global phase of that operation. And so that's why I think the global phase really matters when it really matters in that particular situation, but it doesn't matter as in the global phase of your current state. Like, that doesn't matter because it's physically irrelevant, right? That's what it's written all over the place, I think. And I think with that statement, I'm happy. Yeah, cool. Do we wanna, how much more time do you guys have?
I think I have a meeting to get to, so I probably have to leave.
Yeah, I mean, but at least we got it. I guess at least we got the level 20 solved. That's that's a good one.
Gary to the rescue again.
Exactly.
Well, I was stuck on this for a really long time,
So our voices help you solve the problem. Our thinking voices. Yeah, just it's. I think what Amir said is correct. It's, we were too much fixed on, or we were thinking about the unitary as if like that would be somehow the state of the system, and not, you know what I mean? Like, that's why we couldn't think of even anything close to this. But if you think about it, it makes sense. If you match the state vectors, but the unitary doesn't match, right? Like, isn't it? Can we say that that's the only possibility, or is it too strong a statement?
No, I think that's the correct statement. So it just means that whatever gates you're going to sprinkle in, they're not going to have any effect.
Exactly.
Yeah, they would just be changing potentially the global phase.
And I think that
is exactly, yes. That's something we learned, right?
It's a good intuition. Yeah, it's a good intuition in the sense that yeah, cool. Okay. Cool. Yeah, then I guess we'll plan another one at some point.
Sounds good.
I very much like it. I think it's interesting to have that group discussion.
I think from this, probably the levels that come after will now be easier.
That's what I think.
Until we get to the next hard one, which is like when we get to entangling gates and probably 3 qubits. Yeah. So I think we should all just see how far we can get now.
Exactly.
With this little
let's do that. Let's do that. Let's give us a week or so. Yeah, let's give us a week or so, do 1 hour one, and see where we get stuck. And then once we find one of those where it's like we can move forward, then we do another session. Yeah. I like that.
That makes sense.
Yeah.
Sounds good.
Cool.
All right.
Yeah. Thank you, guys.
See you all.
Stop recording.